Let us discuss this theorem. So in this theorem, we have to prove a set S of which is subset of R is bounded if and only if there exists a positive real number m such that mod of x less than or equal to m. So that means there is a positive real number m such that mod of each element of S is less than or equal to that m. This thing we have to prove. It's very simple. Proof is very simple. Okay. So if and only if part is there, that means we have to prove in both ways. So I am going to consider this part. I will prove that part first. Okay. So I have considered here S is a bounded set. What is meaning of bounded? Set is bounded, that means it is both bounded below as well as bounded above. So I will mention. So implies S is bounded below and bounded above. Okay. So S is bounded below and bounded above. That means it has lower bound and it has upper bound also. So implies S has lower bound and upper bound. Okay. So it has lower bound and upper bound. So I will call it as, let K be lower bound and L be upper bound of S. So therefore there exists K and L belongs to R such that I will mention K less than or equal to X for all X belongs to S. I will say this is 1, and X less than or equal to L for all X belongs to S. So that means this is, we say X is K is lower bound and L is upper bound. Okay, so the given set is bounded, so that's why we could found that lower bound and upper bound. So let us go further, but here we are interested to find m. So we have to find the value of m. So see, I'm defining m in this way. Let m is equal to maximum of mod k mod L. So K is or L positive, negative, we don't know anything. Getting, I'm taking mod for precaution since we want m should be positive real number. So I have taken mod of K and L, and whatever the maximum value, that will be our m. So m is a maximum of both of them. So obviously both of them are less than or equal to m. So therefore I can write, therefore mod K less than or equal to m and mod L, that is also less than or equal to m, since our choice of m is maximum of both of them. So equality is also possible, but can be greater than also. Okay. See, after that, clearly, two facts I am going to write. Clearly, L is less than or equal to mod L. Okay. So L, mod L, that means L can be positive, can be negative. We don't know anything, but mod L 100% positive. So it will be either equal. If L is positive, we will have equality, but if L is negative, we will have inequality. So that's why I can write this one. I will say this is 5 and minus K less than or equal to mod K. So this is 6. This is also in the same explanation I can give, but see, mod, if you apply mod, definitely we will have more value. Okay, that is clear. So let us combine few things. Okay, so from 3 and 5. Okay, from 3 and 5. From 3 and 5. Will you tell me what you'll get from 3 and 5? 3 and 5. 3 and 6. Sorry, 3 and 6. What will you get from 3 and 6? Minus K less than or equal to mod K, and mod K less than or equal to M. If I multiply both sides by minus 1, what will happen if I multiply both sides by minus 1? Minus M less than or equal to K. This is inequality number 7. So you know that when you multiply by minus sign, inequality will get changed. So that's why I could write it. Now, from 4 and 5, will you tell me from 4 and 5? 4, where is 4? This one. Where is 5? Here. Getting? So see, L less than or equal to mod L, but mod L is less than or equal to M. So L less than or equal to M. See, now, you know what I'm going to do? I'm going to combine 1, 2, 7, 8. Let us combine 1, 2, 7, 8. There is no more space to write. So first make a screenshot of it, then we will go further. Okay, so let us combine 1, 2, 7, 8. What will you get? I will start from here, 7. Minus m less than or equal to k. But see, k less than or equal to x. See, x less than or equal to L. But see, L less than or equal to M. And this is true for all x belongs to S. Okay. See, you are familiar with one result, mod A less than or equal to B if and only if minus B less than or equal to A less than or equal to B. So this result we have already seen, right? So therefore, I can use this result here. This form we have got here. So therefore mod x less than or equal to M for all x belongs to S, and so same thing is asked here. Getting, and we proved yes, there exists a positive real number M such that mod x is less than or equal to M for all x belongs to S. Okay. See, make a screenshot of it. After that, we will discuss its converse part. Conversely, we assume there exists a positive real number M such that mod x less than or equal to M for all x belongs to S. We have to prove that here set S is bounded. So see, we are familiar with this result, mod A less than or equal to B if and only if minus B less than or equal to A less than or equal to B. So see, this thing I am going to use here. What will I get? So therefore, see, I am using this result. So minus M less than or equal to x less than or equal to M for all x belongs to S. What we get here? All elements of S are greater than or equal to minus M. So that's why we can say minus M is a lower bound of S, as well as all elements of S are less than or equal to capital M. So therefore we can say capital M is upper bound of S. So I will mention that thing. So implies minus M is lower bound of S and capital M, I'll write this as properly, and capital M is an upper bound of S. Upper bound of S. That is a very important thing we get. That is S is bounded below because of this lower bound, and S is bounded above since it has a upper bound. So therefore S is both bounded below and bounded above. It is both bounded above and bounded below. Okay, so therefore what can we say? It is both bounded below and above. So therefore S is bounded set. Yes, in this way we proved the result in both ways. Okay, make a screenshot of it. After that we will stop. Thank you. Bye bye.